This topic is calculating limits using limit laws. Suppose there exists a constant c and the limit of f of x as x go to a and limit of g of x as x go to a exist as well, right? Then you have the following limit laws. So the first law is the constant law. Right, so limit of a constant as x approaches to a, it is a constant itself. Right, just like the problem we see yesterday, right? So yx, if you have function like this, the step functions as x go to 0 from the right, the function supposed to go to, this is 1, this is let's see, sorry, this is 1, just that, right? So as x approaches a, or x approaches 0 from the right, the function approaches the value 1. Right? So the limit of constant as x approaches a is just equal to the constant itself. Number 2, the sum and difference law. So the first law is the constant law. The second law is the sum and difference laws, right? So for this law, we say that the limit of the sum or difference is the sum difference of limits. Right, so the note here is that the limit of the sum or difference is the sum or difference of limits. Right, so limit as x approaches a of f of x plus g of x is equal to the limit of f of x. So x approaches a plus limit of g of x as x approaches a. And it's going to be the same for the case of minus or difference. Let me write this down. X approaches a of f of x minus g of x is equal to limit of f of x as x approaches a minus limit of g of x as x approaches a. Number 3 is the constant multiple law. If you have the limit of a constant multiplied with a function as x approaches a, it's equivalent to c times the limit of f of x as x going to a. Number 4, product law. So for product law, so the limit of a product and the product of the limits, right? So the limit of a product is a product of limits. So for example, limits of f of x times g of x as x approaches a is equal to limit of f of x as x approaches a times the limit of g of x as x approaches a. The next law should be the quotient law. Right? The limit of a quotient is the quotient of the limits. So I have a limit as x approaches a of f of x over g of x is equal to the limit of f of x as x approaches a divided by limits of g of x as x approaches a. Given that the limit of g of x as x approaches a different from 0. Right, because limit of g of x as x approaches a is in the denominator, you don't want 0 in the denominator, so you have to give that conditions for the quotient limit. Number 6, you have power law. So if you have the limit of f of x to the power n as x approaches a, this is the same as first finding the limit and then take the power. Right. You can either find the power of the function first and then take the limit, or you can take the limit of the function first and find the power. Number 7, similarly, you have root law. So if you have limits of n root of f of x as x approaches a, this is equivalent to finding the limit first and then take the n root of the result. Direct substitution law. So we're going to get back to this law a little bit later, but for now I'm going to give you the formula. So number 8, direct substitution law. Most of the time we just directly substitute the value equal to 8 directly into the function to evaluate the limits. Even though we discussed yesterday or the past few days that for limits, right, you want x approach closer and closer to a, but never going to be a. Right? However, in practice, you can use direct substitutions laws to evaluate the limits. Right? It's a lot easier. So direct substitution law. So you have the limits of x as x approaches a. What is the value? Right? So you just substitute x equal to a and you get the value of the limits. So this is equal to a, right? Because x equal to a, so that's why. Another example is that if you have a power function and you let x approaches a, what you can do is you let x equal to a and the answer is a to the power n. And similarly, you have the limit of n root of x as x approaches a is n root of a. Right, as I mentioned, we're going to get back to this direct substitution law a little bit later. For now, if you want to find the limit of function, just let x equal to a. Even though, like I say, we discussed about this and we want x approach closer and closer to a, but in practice, it's a lot easier to just let x equal to a. All right, so we have 8 different laws, 8 different limit laws, right? Constant law, sum and difference laws, constant multiple law, product law, quotient law, power law, root, and direct substitution laws. All right, so let's do some example on this. Evaluate the limits and justify each step. So part A, I'm going to do, or problem A, I'm going to do limit of 2x squared minus 3x plus 4 as x equal to 5. Now what you can do is you can rewrite this limit as limit of 2x squared x equal to 5 minus limit of 3x x equal to 5 plus limit of 4 as x equal to 5. Right. For the first 2 terms or first 2 limits, you can see you can also could be able to apply the constant multiple law. Right? That means you can pull the 2 out of the limit operations. You have 2 times limits of x squared as x go to 5 minus 3 times limit of x as x go to 5 plus limit of 4 as x go to 5. So what I can do is, so this, I'm going to justify my step. So this is difference. Right, so this is sum law. This is constant multiple law. Right, so it's the same thing for the second term. So constant multiple. Right, and the last term we have not made any changes yet. Right, for this evaluation, like you can use direct substitution law. So very straightforward that you have limit of x squared as x go to 5. That means the limit is 5 squared. Because you have x squared and x is equal to 5 minus 3 times 5. And the limit of a constant is the constant itself. So this is plus 4. Right, so you have 2 times 25 minus 15 plus 4. This is equal to 50 minus 15 plus 4 minus 11, 39 for the answer. Right. So the question is, do you have to justify each step like this? You don't have to. This is the very first example in evaluating the limit of the functions using limit law. So that's why it's good for you to see this kind of problem in actions, right? So what kind of law that I'm using, right? And what is the step that you need to have, right? In practice, in real life, you don't need to write limits like this. Like nobody cares about limits, limit after limit after limit. But in mathematics, we do, right? We do care about the notations. We try to understand what is the proper procedure for getting the results, where you get the result, how to get the results, right? So it's good that you keep writing the limit for each step of the problem until the step of evaluating the limits, right? When you let x go to 5 or x equal to 5, you stop writing the limits, okay? But before that, before evaluating the limits, you have to keep the limit notations at all time, okay? So I'm going to go back. I'm going to remind you over and over again to keep the limit notation until the evaluation step. Right, so this is the evaluation step right here. And so therefore you see there's no limit notation anymore. Get back to the idea of justifying each step. After a while, you don't have to. Like I said, this is the first example. So I want you to see what kind of law I'm using. All right. Part B, limit of x cubed plus 2x squared minus 1 over 5 minus 3x as x approaches negative 2. Right, so this is the quotient. Right? So the limit of quotient is quotient of limits. So what you can do is limit of x cubed plus 2x squared minus 1 as x approaches negative 2 and divided by limits as x approaches negative 2 of 5 minus 3x. Right, once again, this is the quotient law. Limit of a quotient is the quotient of limits. So on the numerator, you can write limits of x cubed, x approaches negative 2, plus limit of 2x squared as x approaches negative 2, minus limit of 1 as x approaches negative 2. So that is the numerator. For the denominator, so in the denominator, you have a limit of 5 as x approaches negative 2 minus limit of 3x as x approaches -2. All right, so you can evaluate term by term, for each limit, right? And so on the numerator, the limit of x cubed as x goes to -2 is -2 cubed plus 2 times -2 square minus 1, right? Limit of a constant is the constant itself, divided by limit of 5 as x goes to -2 one more time. Limit of a constant is the constant itself. So you have 5 minus 3 times -2. So what do you get here? So -8 plus 8 minus 1, 5 plus 6, so -1 over 11. Right. So one more time, you have to keep writing the limits, right, for every single step until the last possible moment or before the evaluations of the limits, right? So this step right here is the evaluation of the limits. So that's why there's no limit notations anymore. But before that, limit notation for every term, right? Limit notation for every term. Just be careful with that. I know it's time consuming to do, but it's a good thing to do because we're in the mathematics class and we want to be mathematicians, right? So let's keep it that way. So that's it for this kind of example. We're going to see more and more of this example along the way, but I'm going to move on to something called direct substitution property, right? So go back to the idea of direct substitution law. If f of x is a polynomial or rational functions, and A is in the domain of f, right? So that means the function is defined at that point, right? Defined at that point A. Then limit of the functions as x approaches A is equal to f of A. This relations right here has a deeper meaning. It's called continuous function at A. The function is continuous at A, right? So functions f of x is continuous at A, right? So that's the deeper meaning. It's not only the direct substitution property, but also you are allowed to do that because f of x is continuous at A. Right? However, right, there's always the however. Not all limits can be evaluated by direct substitution property or direct substitution law. Not all limits can be evaluated by direct substitution. Right, so you will see in the following example. So example, evaluate the limits. Limits as x approaches 1 of x squared minus 1 over x minus 1. If you just use direct substitution, what you're going to get, right? Using direct substitutions, what do we get? So you have limit of x squared minus 1 over x minus 1 is what? 1 squared minus 1 over 1 minus 1. You have 0 over 0. This is called the indeterminate form, right? So it's kind of, in a way, it's undefined because you're not sure what a 0 over 0 is going to be. right? So therefore, you cannot get the limit from this. The limit does not exist in the sense of direct substitutions. So when you see something like this, you have to manipulate the function so that you avoid this type of indeterminate forms. Okay. So if you notice this function x squared minus 1 over x minus 1, there's a way you can make the cancellations, right? So x squared minus 1 is what? X minus 1 times x plus 1. So before using direct substitutions, what I can do is I'm going to simplify the functions. So x minus 1 times x plus 1 over x minus 1. Right, and you see that x minus 1 cancel out, and you're left with limit of x plus 1 as x approaches 1. So therefore, you have 1 plus 1 equal to 2. Now you can use direct substitutions because you get a constant at the end of the evaluations, not the indeterminate form. So next example, limits of 3 plus h squared minus 9 divided by h as h approaches 0. Right, first, do direct substitutions. By direct substitutions, you get this. So you get 3 plus 0 squared minus 9 divided by 0. You have 9 minus 9 over 0 or 0 over 0. So one more time, you get something called the indeterminate form. So you don't want that, right? So you have to somehow simplify the function so that you can avoid this indeterminate form. So once indeterminate form. So before direct substitutions, before using direct substitutions, what you can do is you simplified the functions, right? So the functions, you have a 3 plus h squared minus 9 divided by h. What you can do is you can expand the 3 plus h squared, right? And you get 9 plus 6h plus h squared minus 9 altogether divided by h. You see that 9 and negative 9 cancel out. You left with limit as h approaches 0 of 6h plus h squared over h. And you can simplify further. On the numerator, you have h as the common factor. Now you can cancel out the h. You're left with limits as h approaches 0 of 6 plus h, or 6 for the answer. Let's move on to another example. Evaluate this limit of square root of t squared plus 9 minus 3 divided by t squared as t approaches 0. Right, first I'm going to do direct substitutions and then see what we got. Right. always try, right? Even though you see a lot of limits that you cannot apply direct substitutions immediately, but most of the time, try with direct substitution first, right? It works, so that's why we try it first. When we run into the problem, just like we are seeing right now, then we do some simplifications. All right, so by direct substitutions, you have limits square root of t squared plus 9 minus 3 over t squared as t approaches 0 is equal to square root of 9 minus 3 divided by 0 squared, or 0 over 0. Once again, this is the indeterminate form. So therefore, you have to do something else. You have to do some simplifications. So before using direct substitutions, so this is the limit that we have. So for this particular problem, how would you get rid of this indeterminate form? Right, so most of the time, for the previous two cases, what you can see is we try to eliminate or cancel out the term in the denominator. Right, so for this particular problem, we try to get rid of h in the denominator. For the previous problem, we try to get rid of x minus 1 in the denominator. So with that idea, we're going to move on to our current example, and we say, can we get rid of t squared? Because there's a 0 in the denominator and you don't want that to happen. So to, in a way, get rid of t squared, you're going to radicalize these functions, right? Because we have a square root in the functions. So radicalized process is that you multiply and divide by the same term of t squared plus 9 plus 3. This is square root of t squared plus 9 plus 3. The idea, just multiply and divide by the counterpart or the conjugate of square root of t squared plus 9 minus 3. And after that, so top multiplied by top, bottom multiplied by bottom. You have t squared plus 9 minus 3 times square root of t squared plus 9 plus 3. And divided by t squared times square root of t squared plus 9 plus 3. Right. For the numerator, you can see that is the difference of two squares. Right? If you use a squared minus b squared, you have a minus b times a plus b. Right? That's the formula for the for the numerator. And so therefore, you can rewrite the numerator as this. Right, so square root of t squared plus 9 altogether square minus 3 square. Divided by t squared times square root of t squared plus 9 plus 3. You have t squared plus 9 minus 9. You have t squared times square root of t squared plus 9 plus 3. Positive 9, negative 9 cancel out. So that's what you get. Now at this step, you can simplify or cancel out the t squared just like we want, right? So you're left with the limit as t go to 0 of 1 over square root of t squared plus 9 plus 3. So now you can do direct substitutions, right? So let t equal to 0, and the answer should be 1 over square root of 9 plus 3, or 1 over 3 plus 3, which is 1 over 6. I'm going to recap what we learned today. So today we look at limit laws, right? Calculate limits using limit laws. You have 8 different laws: constant law, sum and difference laws, constant mutable law, product law, quotient law, power and root laws, and one of the most important laws is direct substitution law. So we did some example on evaluating the limit of the function using these limit laws. And for direct substitution property, right, you could be able to do all of this because of the idea of f of x is continuous at a, or a is defined in the domain of the functions. However, not all limits can be evaluated by direct substitutions, right, unfortunately. You have to look at the problem more carefully. If you use direct substitutions at the first step, there's a good chance you run into the problem of getting the indeterminate form of 0 over 0, right? So when you run into that problem, try to simplify the function as much as you can, right? Especially try to get rid of the denominator, right? So we did the 3 examples related to that. So I think that's it for today.